Are there any questions? Finally got Noah.
I had 1 over x minus 1 cubed. I thought it would just be like 1 over x cubed, but translate to the left of it. And so I thought it would diverge, but it doesn't.
Are you integrating from somewhere to somewhere?
From negative infinity to -1, or from 0 to infinity. I have all those problems.
You need a different function if it's from 0 to infinity. You need a different function. I mean, you say you had both of them the same problem, just 2 different versions of it, or 2 different problems?
Well, 2 different problems. So like it was 1 over x minus 1 cubed. One of them was from 0 to infinity. One of them was from
0 to infinity?
Yeah.
I have not shown you how to do this one.
Oh, and x plus 1.
Ah, x plus 1. I have shown you how to do that one. You might say, well, what's the difference? Well, we'll talk about it before the day is over. It converges. I can pretty sure of that. Let's work it out. Maybe not all the way out, but far enough we can see what's going on. To set it up for an antiderivative, I'm going to write it as x minus 1 to the minus 3. Okay? And substitute. We can't really raise it to the 3rd power. That wouldn't help one bit because it's in the denominator. But we can substitute. And really, I hope you can like do this step in your head because something about it is super nice. And maybe I'll write the details and then I'll show you how I'd like you to be able to think about it. See, if I substitute for that, then I just have u to the minus 3. Which is an obvious antiderivative. Raise the power divided by the power. Because the derivative of the inside function is 1, right, there's no constants to bounce around. So I can look here and say, well, the derivative of the inside is 1. If I had a 2 there, then I would say, oh man, I've got to deal with that 2. And u would be 2x minus 1 and du would be 2, right? And so we'd have to deal with it 2. But man, when the derivative of the inside is 1, then all we have to do is raise the power divided by the. So the limit as a goes to minus infinity. X minus 1 to the minus 2 divided by minus 2, and we will go from a to -1. Take that negative 1/2 out. I always do that. I take the constants out. I believe it makes life easier for us. And then the 1/2 is gone. We're left with this thing. And of course, that's the same as 1 over x minus 1 squared, right? So let's plug in our -1. I get 1/4. -1 minus 1 is -2, squared is 4. And then I get minus the limit. I'm sorry, I already got the limit. Plug in a, I get 1 over a minus 1 squared. Right? As a goes to minus infinity, what the only a that shows up is right here. What does it do? 0. Goes to 0. The bottom's going to infinity. 1 over infinity. So what's the answer? I believe it's actually -1.
I didn't see that.
Yeah, we took it out and maybe it's kind of high. As soon as x gets below 1, this function is negative, right? X minus 1 would then be negative, cube a negative, you get a negative. So we definitely need a negative answer. And maybe when we get the negative answer, like it gives you pause. Think about this function. You know, we're going to minus infinity. So once we think about it, it would give us pause if we didn't get a negative. Oh, we did. So to answer your question, Noah.
Yeah, and then for the positive one, I tried breaking it up into a over x plus 1 plus b over x plus 1 squared, and c over x plus 1 squared.
Okay, that's way too complicated. It's the same as this one. The derivative of the inside is 1. So this is just exactly like u to the minus 3 power. Raise the power, divide by the new power. Okay?
But you could do it that way too, right? If it was,
The way that you suggested? Okay, so tell me again.
I said x plus a over x plus 1 plus b over x plus 1 squared plus c over x plus 1.
Oh, I see why you're using our technique, which is good thinking for you. Some of the time, maybe not all of the time, but some of the time when I wrote down a new antiderivative for us to find out, I would say, do we know an antiderivative already? Do we not need some fancy technique? Okay, and if we don't, I mean, if we do know one, let's not use the fancy technique. But, you know, maybe you missed it. So this one is, you can just go right here by that substitution. So, okay, so let's talk about this a minute. So Noah says, and you know, why not? We just learned how to do it. We're going to do a partial fraction decomposition. And it's a case 2, a linear repeated. What do you think is going to happen? What do you think A is going to be? We need those functions to be exactly the same.
It'd be x plus 1.
Well, A, B, and C are constants. They can't depend on X. Constants. What do you think A has to be? For that function to equal that function, A has to be it can't have it's a constant. It's like 17 or -5 or the square root of 13. It's something like that. What does it have to be? The only thing it can be. 1?
-1.
-1? So I need this function to be exactly the same as this one. Can you make that happen? Yes, if A is 0, and if B is 0, and if C is 1. That's what partial fractions is going to tell you. This one's got to be 0. This one's got to be 0. This one's got to be 1. And therefore, where are we? We're right back where we started. Okay? You believe me? Yeah. All right. Anything else on the homework? I was getting ready to say, oh, Scott.
Oh, were you gonna say something else?
Pardon me?
Were you gonna say something else?
I can say it later.
I was just gonna ask, like, if on an exam, well, like on my homework, instead of resubstituting my my u for x minus 1, I just reset my boundaries.
You can always do that.
Okay.
Yeah, now it looks a little funny when we have a variable like it's going to be a plus 1 or, but as long as you're careful, you can do that.
Okay.
Take it.
You said if you can't do the derivative of infinity, it's x minus 1.
Yes,
Why?
because if this was a -1, what happens to that function at x equals 1? It shoots up to infinity, right? Okay, and we don't know how to integrate functions like that. Now, how do we know you haven't? Well, we've carefully avoided them. because you can't form a Riemann sum really. I mean, you can't, there are actually two kinds of improper integrals. All of our work so far has been focused on the first kind, where infinity shows up as one or both of the limits. Okay. Today we're going to talk about the other kind, which is where the function blows up to infinity on our end. Okay, and that's what happens here. Any other questions? I was going to say something, wasn't I? Oh yeah. Wasn't it nice after a couple of sections with no online homework to finally get some? And I went a little bit overboard, didn't I? They gave me so many. I think I signed, actually I signed 15. And then I thought, well, I don't want people hating me. Right? And what I mean by that is other professors, because I know you guys would love, like, man, 15, bring it on. Like, how about 20? But then, you know, your physics professor would be mad at me. And we couldn't have that. So I got rid of some of that seemed to be, but it was nice to have some that can, so that you can get the feedback as you're working through the problems. And I've already posted, maybe you've seen the assignment. There weren't quite as many over the second kind of improper integral that we're going to talk about, but I think I was able to get you somewhere between 5 and 10. All right, so I want to talk mostly about this other kind of improper integral today. But first, I want to look at a whole class of functions. So we're going to call this a P integral. The integral, I'm going to start at 1. The 1 actually doesn't matter. We'll talk a little bit about that. 1 over x to the p. The p is a number. Because, you know, the x is in the denominator. This improper integral, the only chance it has to converge is if p is a positive number. If p is a negative number, like just pick your favorite negative number, -2. 1 over x to the negative, that's like x squared. And that function all by itself is going to scream off to infinity, let alone looking at the area underneath it, right? So for this to have any chance, in fact, let's say it this way. If p is less than or equal to 0, it diverges, and it's not even interesting. If p is positive, then it has a chance. At least the function dies out. Okay, and we actually did at least one of these on Friday. So if p is positive, 1 over x to the p goes to 0, which gives it a chance. And now we want to investigate. I could draw a generic graph for all of those. We've got, it's undefined at 0, so we've got a vertical asymptote. And the 1 doesn't really matter where we start. We could start at any positive number, but I'll just put 1. So you can see it has a chance. This is for all the positive p's. You know, it would be slightly different if we changed the p, but the same idea. It would die out. It would have a vertical asymptote of 0. If p equals 1, it diverges. We showed that on Friday. That is 1 over x. Remember, we got the log function. So it diverges. For any other positive p-value, to evaluate that, we're going to deal with this antiderivative, which raise the power by 1, divide by the new power. Right? That's our antiderivative. So for that to converge, we're gonna need. We need those x's to go down in the denominator, take it.
So if people want to know, why can't you say that P is less?
Well.
Because when you say it's positive, then you're like, oh, just kidding.
Yeah, so maybe, we haven't shown it yet, and so maybe in theory, it could converge everywhere less than one and everywhere bigger than one, just not at one. Because it's at least theoretically possible. We haven't investigated any particular case except for P equals 1. Now, if I understand your question, you're going to be proved right in just a minute. Okay?
But then if I can insert a careful, why is it saying P is less than or equal to 0, 1 is 1? Because then you say if P is bigger than 0.
Oh,
Does that?
okay. Oh, I understand your question now. All right, so think of the p-axis. So, here is p equals 0, and here is plus infinity for p, and here's minus infinity. So over there, I said just because of the nature of the function, we know it diverges there. Okay, and then on class, we picked one case and we showed it diverges there, but we haven't really investigated what happens everywhere else. Okay.
That makes sense.
Yeah, super good question. I'm sorry I misunderstood it, but thanks for sticking with it. If it's going to converge, we need those x's to be in the denominator, right? So that when x goes to infinity, it's going to die out. You with me? 1 over infinity, that's going to 0. Okay? Well, another way of saying that, comma, or we need p to be less than 1. Greater than 1. Can't read my own writing. Thank goodness. Add the p across, so p greater than 1. If p is between 0 and 1, the function goes to 0. But after we find the antiderivative, we add 1 to that power. Now it's back in positive territory, right? But think 1 over the square root of x. It goes to 0, maybe it's got a chance to convert. But 1 over the square root is x to the minus 1/2. Add the 1 and that negative 1/2, what happens to it? It turns positive. So that is going to go off to infinity. So we've satisfied it. For convergence, we need that to be true. And then this function is going to die out. Okay, so we'll finish it in here. It diverges here as well. But if we can get bigger than 1, it converges. So 1 is the separation point. And 1 actually goes the diverging direction. But if p is bigger than 1, it converges. We add 1 to a number that's more negative than -1. When you add 1, it's still negative. And so it's going to die out in the limit. So let's summarize with what we're going to call the p integral theorem. The integral from 1 to infinity, 1 over x to the p dx converges. In fact, I can even write a formula for it. I'll do it in just a minute. I'll do it right this minute. I haven't shown you this in class, but it's true. It equals converges to 1 over p minus 1 if and only if p is greater than 1. If and only if means if p is bigger than 1, it converges. If it's not bigger than 1, it doesn't converge. It tells me the result for every value of p. So to justify the value here, we can bring our antiderivative back down here. At infinity, it's going to die out, and then we're going to subtract the value at the lower endpoint And so the 1 minus p is going to survive, but because it's the lowering point, it's going to be the negative of it, which flips it around to 1 over p minus 1. So for example, the integral of 1 to infinity, 1 over x cubed dx, does it converge or diverge? P is 3, bigger than 1, it converges. What does it converge to? Yeah, 1 over 3 minus 1. 1/2. I believe I'm off the screen. Here you go, David. So he can pause that and get what he needs. What about this one? The integral from 4 to infinity, 1 over x to the 5th. I changed the bottom limit from 1 to 4. Is that going to affect whether it converges or not? It is not. There's a finite amount of area from 1 to 4. And so we're going to take the p integral, p equals 5, is that converge or diverge? Converges, sure, it's bigger than 1. And if we started at 1, we would know it converges to 1/4. Well, because we're not starting until 4, it's going to converge to a number smaller than 1/4. And we could work it out. It's easy. But I don't want to do it. We'll just say it definitely converges. And when it converges, and especially if I haven't worked out the exact value, I'll just say it's less than infinity. That's a nice, easy way to say that. I could even do something like a 1/10 to infinity 1 over x to the, I don't know, squared. Actually, let's do x to the pi just for the fun of it. So we start integrating at 1/10, not at 1. Well, how much area is there between 1/10 and 1? Is it a finite amount or could it be an infinite amount? Yeah, it's a finite amount, 1/10. You know, we're getting closer to this asymptote, but we're not there yet. So we're going to take the p integral for pi is bigger than 1, so it converges. Okay, and if we started at 1, it would converge to 1 over pi minus 1. The fact that we're starting 1/10 means it's going to converge to a little bit bigger number, however much area is in this little slice right here. Okay, so it converges. And the number a little bit bigger. And we can work it out. I mean, it's not hard. We know what the antiderivative is. We can plug it in and do the arithmetic. All right. Jesse.
What happens if it's 0?
0 is a problem because now we're hitting right against that vertical asymptote. And we're not yet prepared to talk about it. But this line right here means we're going to change the subject. And we're going to address that exactly. Okay? All right. It turns out there are 2 types of improper integrals. I've said that before. I haven't made it formal on the board. I didn't say it at the beginning of this section because in my experience, and maybe, I don't have a very good experience. I mean, it's sort of narrow. It's not everybody's experience. But the first kind of improper integral I use a lot. I teach probability and almost all of our functions we work with there. We have to integrate. We can define probability as being area under the curve. And so we're always integrating. And most of the functions, they go off to infinity, at least positive infinity. And some of them go minus infinity, plus infinity. So I work with those kind of integrals all the time. And, because I have that bias, I want you all to understand how to do it as well. I don't so often see the second type, but I want you to know about it. We should know about it. And besides, we want to answer Jesse's question. So let me summarize 2 types of improper integrals. The first kind, which we're now experts on, or we're working at, I'm gonna say they're improper because they are over an unbounded interval. Infinity gets involved. Second kind have an unbounded integrand. I don't know if I've used that word before. Let me tell you what it means. No, on all of our integrals, whether indirect, antiderivative, or direct. It's not the right word. Definite or indefinite. We have this integral sign, matches the dx, and in between it, there's a function, right? Well, that function is called the integrand of the integral. And so what we have is a function that is unbounded on the interval, which our generic interval is a to b. Unbounded means the values go off to infinity. You can't bound them. So there's something like a vertical asymptote. It can be at the left-hand endpoint, the right-hand endpoint, or it can be anywhere in between. We've seen a couple of them. Noah asked a super good question to illustrate this at the beginning of the class. Remember, he said he wanted to know something about 0 to infinity, 1 over, maybe I don't have the right one, but something like this. And I didn't like it very much. It has both types of improper integrals embedded. Obviously, the first type, I mean, those are obvious. There's an infinity somewhere at the top or the bottom or both. But what happens to this function at x equals 1? It's undefined. Why is it undefined? It's shooting off to infinity. Okay? And the trouble with that is 1 is on this interval. If I just bump this over to 2, now it's no big deal. I'm staying away from that bad point, that unbounded boundary. But the problem that Noah gave me, the place where the function was undefined, where it's shooting off to infinity, was on our interval. And so this actually incorporates both. And when he asked the question, we weren't ready to talk about it. And then he realized, right, that you ask it wrong and we got it corrected so it fit the type we did. Yeah. All right. So let's say the problem is at the left-hand endpoint. So our picture looks something like this. We have our interval A to B, and over here we have a vertical asymptote. Shooting up to infinity, the closer we get to the left-hand endpoint A. And so here's how we deal with it. The improper integral A to B f of x dx. I'm going to convert it to a limit. If I can stay away from A, maybe only integrate to there. Let me call that T. It's like a temporary resting point. If I could just stop short of A, no problem. We have a proper integral. And so we're going to integrate from T to B, f of x dx, and write that integral as a function of T, if we can do it. That is, if we know the antiderivative. And then we just need to take the limit of that function as T approaches A from above. Okay, that's how we're going to handle it. It's the right-hand endpoint in an entirely analogous way. The integral from A to B, f of x dx. And think of the limit as t approaches b from below, the integral A to t. problem is at the right hand, at the other side. If it's in the middle, or it's an interior point, and let's say it happens at C, comma, A strictly less than C, strictly less than B. Well, maybe the picture looks like A, B, C. There may be something like that. Could both, one up, one down, both up, both down, doesn't really matter. Then we're going to write the integral, the way we deal with it. Equals the limit. I'm going to break it into two integrals. One of them where the problem is at the right-hand endpoint, and another one where it's at the left-hand endpoint. And we know how to deal with it. In fact, I don't think I need to write the details because we know how we deal with the left, we know how we deal with the right. Let me say it this way. Evaluate the integrals, the improper integrals over the two parts of the interval. A to B. Those parts are A to C, and then C to B. If they both converge, converting them to a limit, so we're going to get a value that converges or not. If they both converge, the integral, say it. And by it, I'm talking about, there it is. Well, there it is. Converges. If either one of them diverges, the integral diverges. Otherwise, the original integral diverges. Okay. So let's say I'm interested in this integral right here. And so I set up my first integral from A to C. And the problem's at the right-hand endpoint, so I convert it to this limit right here. I evaluate it and I find out it diverges. I'm done. It doesn't matter what happens over here. Right? For it to converge, they both have to converge. If I pick one and it diverges, then I'm done. I'll say it diverges, not interesting. If I pick this one and it converges, well, then I need to go over and look at this one. This thing's always taking me. If it converges, then the original integral converges to their sum. If one converges to 5 and the next one to 7, then the overall converges to 12. If this one converges to 5 and this one diverges, that guy diverges. Right? They both have to converge. And then we get a value, we can add them up because we're integrating over the two parts of the interval. Are there any questions? Does it make sense to you? Yeah. Here's an example of a type 2 improper integral, 0 to 1. One over the square root of x. This function is only defined on positive numbers. As x approaches 0, the denominator approaches 0, which is making the fraction blow up, right, to infinity. Picture of what's going on here is sort of like that. And arbitrarily picked one. So we're asking like, how much area in there? And it's an unbounded region. Our function is shooting off to infinity. I probably taught somewhere around 40 sections of Calc 2 over the years. And this is my last one. I'm retiring at the end of this semester. And always in the past, I've talked about second type of improper integral, and I've always just sort of grinded out a solution. But over the weekend, I had this, shows you can always learn new things. I had this sort of epiphany that, oh man, instead of grinding through the details, we can use something we've already learned to analyze this integral. In fact, it's going to be P integrals, except instead of looking at the infinity side, we're going to look at approaching zero side. 1 over x to the P, if P is positive, all of those have a vertical asymptote, right? They're all unbounded on the interval 0 up to wherever we want to go. And so I had this epiphany, like, oh man, I can use what we've already learned rather than, how many times have you heard somebody say, don't reinvent the wheel? So we invented the wheel earlier with our P integral theorem, and now we're just going to use it rather than reinvent it. And the amazing thing is that in my class this morning, one of the students, he said, well, can we use that thing we learned on Friday? He had the exact same epiphany that I did. He got it maybe the first time using Calc 2, and it took me 40 tries before I got it. But that's what we're going to do. And what he said was, look, there's a graph. I'm going to do it generically, not for the 1/2 power. We'll say, here's a function 1 over x to the P. And again, to be interesting, we need P to be a positive number. And his insight is, and maybe some of you have it, but the pressure's on. I'm going to keep up with that student and his brilliant insight. Look, why don't I think about functions of y instead of functions of x? And then this improper integral, what happens to it? So there is an issue, like we're going to have to deal with that square right there. But if I think of functions of y, then finding the area here, it becomes exactly like the kind of integral we've already learned how to solve, right? We're going to go from 1 to infinity. By using functions of y, it turns it into a problem we've already solved. Okay, so that was his suggestion, and I thought it was absolutely brilliant. So x to the P, we're going to use functions of y. We've done it before. If we've never done it before, then we probably never. In fact, I think the student that made the suggestion, I think he said we should do what we did before, like with areas and volumes. In fact, we got kind of good, didn't we? At least hopefully, at looking at a problem and deciding, should I use functions of y or x, like based on the nature of the area. And if it's a volume, is it going around the x or the y? What's going on? And we do the same kind of analysis here. So I need to solve for x. If y equals 1 over x to the P, x to the P equals 1 over y. Take the P root. And simplify 1 over y to the 1. And so start at 1. That function is going to converge if what is true. Converges if and only if. We mathematicians have an abbreviation for if and only if, IFF. If and only if means, in connection with the P integral theorem, we say the integral converges if and only if P is bigger than 1, means if P is bigger than 1, it converges. It also means if it converges, then P has to be bigger than 1. It goes both ways. And the same thing here. So that's a P integral, right? And it converges if its value of P, so to speak, is bigger than 1. Well, what's the value of P after we solve for Y? P in quotes. What is Y raised to? Pardon? The exponent on Y, that's how we find it.
Raised to 1 over P.
It's 1 over P. Yeah, this is a, now, we're using the same symbol. The way we started, P made perfect good sense. And now we convert it and we have to kind of think, well, how does it work? That is, if the P value here, which happens to be 1 over P, bigger than. You see that? And if you solve that inequality, multiplied by P, we get that P has to be less than. Well, we already said it had to be positive. If it's negative, it's not an improper integral. If the exponent, it's not an improper integral, it's a proper one, therefore it has a value. To be improper, we need P to be positive. And then it turns out we need it to be less than 1 for convergence. So when I integrate from here, I get a finite value. In fact, our formula works. And this integral, it's all of that area, plus it's this little region here, which happens to be a square. It has a finite amount of area. So it's going to converge. We get this piece, which we can write as a P integral, and we got, as long as we have the right P value, and we do here, what's the value of P here? 1/2, it's in the good range. It's between 0 and 1. So this guy converges. Okay, and then we get that starting from here and going out over here says it converges, then we just add 1 onto it. If this integral converges to 12, this one converges to 13, because we have this little square at the bottom, which is counted here, but not counted there, right? All right, so here's the P integral for second type, the P integral theorem. I'm not going to use those words because I don't want to confuse it with what we already have said. And like I said before, the first one is going to be more important to us. So here's our result. The integral from 0 to 1 over x to the P dx converges as less than infinity if and only if P is between 0 and strictly between 0 and 1. Okay. Some results of that. If P equals 1, what about this guy? What did we decide about it? What's the value of P? 1. Good or bad? Converge or diverge? Bad. How about if we go from 1 to infinity? 1 over x dx. Good or bad? Converge or diverge? Diverge. May feel bad. So 1, the power, P equals 1, both sides converge. You see what I mean by both sides? This side over here and this side over there. They both are infinite. But if I can bump P off of 1, 4. The integral from 0 to 1 over the x to the 4th dx, and the integral from 1 to infinity, 1 over x to the 4th dx. What have we figured out here? Which one of those converges? Top? The bottom. Yeah, P equals 4. So this one, in fact, I showed you what it converges to, if you believe me. 1 over 4 minus 1. This one diverges. Right? We need P to be between 0 and 1. 4 is greater than 1. That's no good. About P equals square root of 2 minus 1. So we'll go from 0 to 1, 1 over x to the square root of 2 minus 1 dx. And then we'll go from 1 to infinity, 1 over x to the square root of 2 minus 1 dx. Which one of those converges? The one on the left. How come, Scott?
Well, because the square root of 2 minus 1 is going to fall into that range.
Square root of 2 is 1.4-ish. Take away 1, 0.4. Yeah, this one's finite. This one diverges. Square root of 2 minus 1 is not bigger than 1. For the first type of integral, we need it to be bigger than 1. I hope I have time for one more example. I do. I declare. All right, we spent maybe too much time with these P series, but we got it all figured out. We're experts. Let's try a totally different one. 0 to ln x dx. Julian,
When you say that it's less than infinity, it's saying the same way.
it converges. It's a shortcut way of saying it converges. We can find the value, absolutely. I think it's 1 over 1 minus p. But that's not important to us right now. Why is this an improper integral? Yeah, in particular, what is it about ln? As x approaches 0, ln goes to infinity, negative infinity. Yeah, most of you are in my Calc 1 class, and I preached to you back in September. Like, you should know the graphs of all of these functions, and ln x looks sort of like that, and I'm sure you remember, just need a little jog. So there's the problem right there. It's shooting down to minus infinity. All right, that's the left-hand endpoint. So we're going to convert it. We have a technique. When I'm writing all the symbols out, t was handy. But now let's do what we did for the first. I'm just going to say let a slide into 0 from above. Then we'll integrate from a to 2. I don't need an extra variable. Okay, so the problem here is at the right-hand endpoint, and we worked out those details before, and now we need an antiderivative. How about, what do you think? An antiderivative of ln x. Any theories? So on one of the videos I posted when I was gone, it may have been the video that at the end of it, it said, for those of you who read this far, send me a happy Valentine's Day message and I'll bolster your homework score a little bit. And 2 or 3 of you actually found that and sent me a message, so good for you. It was on integration by parts. And one of the examples I gave was that, I mean, at the end I said, we can use integration by parts to fill in some gaps. Like at that point, we had never seen a function whose derivative was the inverse tangent. Therefore, we didn't know the antiderivative. And I did the log as well. So we're going to integrate by parts. I'll go quickly here. I think it's still on posted if you want to go watch it. And so we get still inside the limit. And the antiderivative is uv x ln x minus the trade-off, the integral from a to 2 v to u. Well, notice the x is just canceled. So we just get dx. And that's an easy, couldn't ask for it to be any X ln x minus x. Made it 2. Which equals. And no problem at the 2 ln 2. Problem spelling ln minus 2. And then something really interesting. Minus a ln a minus a. So the antiderivative in the end is x ln x minus x. So we plug in the upper limit, plug in the lower limit, subtract, just like the fundamental theorem says. And now almost everything here is really nice and obvious. This is a constant. It's going to survive. This piece right here, as a goes to 0, what happens to it? Limit of a as a goes to 0. It goes to 0. I mean, it's the same variable. The only question is a ln a. So let's pull it out and analyze. The limit as a approaches 0 from above. A ln a. Notice that has the form 0 times infinity. The log goes to infinity. A is going to 0. And this is an indeterminate form we learned in Calc 1. And so what we need to do is use L'Hopital's rule. But I need a fraction. And that's easy to get. I'll just pick one of the factors. I'm going to pick the simplest one and throw it down in the bottom. I can't just move it to the bottom. That would be a different function, but I can move its reciprocal to the bottom, and now it's the same. And now this goes to infinity over infinity. So we can use L'Hopital's rule. Approaches 0 from above. We take derivatives. 1 over a in the numerator. Negative 1 over a squared in the denominator. Take the minus sign out. Simplify, we just get a. That a squared kicks up above, cancels out the a. That's already there. And the limit is 0, amazingly enough. So our answer is 2 log 2 minus 2. It converges. So how much area trapped? Actually, we went clear over here to 2. So when we add this piece to that piece, it converges, and we actually have 2 log 2 minus 2. Is there more area above the x-axis or below it? Is our answer positive or negative? 2 log 2. Is log 2 bigger than 1 or less than 1? So what's the log of e? 1. Is 2 bigger than e or? Yeah, that's a negative number. Log 2 is less than 1. Therefore, 2 log 2 is less than 2. And then so take that number, which is positive, subtract 2, makes it negative. Doesn't matter, you could ask the calculator. All right, I went late, I apologize. I'll give you a bonus someday because of it. Thank you for patiently waiting. And believe me, I